Okay, guys, so the last thing we're going to talk about in section 9.3 is a special case of working with means. And what we call this is called paired data. So back when we were talking about the different types of studies we have and all of that, we came across something called matched pairs, a matched pairs experiment, where we were either pairing up people as similarly as we can, like based on height, weight, gender, and all that sort of stuff, and we took those results and we compared them, or we took a person's results from one part and I compared it to that same person's results in another. And the data that we get from that is what we call paired data. And so a special case of running a means test. And so we use this because a lot of times comparing data is way more convincing than just using one sample. So one sample of data may be okay if we have kind of an idea of what's happening. Like someone claims to be an 80% free throw shooter, but we want to test and see if it's true or not. But sometimes we want to see, does a medication actually work? So we may pair people up and test them, test one person on one medication and one person on another, and we look to see if there's a difference, if one medication is more powerful than another. Or we may pair people up and one person doesn't get a medication, they get a placebo, and the other person gets a medication. We look to see if there's truly a difference. So with that in mind, using a one sample data is usually less common than this idea of comparing data. So we would then be looking at study designs that involve making two observations on the same individual, or one observation each of two similar individuals, resulting in that paired data. So again, that matched pairs design. Now, when paired data result from measuring the same variable twice, we can make comparisons by analyzing the differences. So we're still really analyzing one set of data because we've taken the two set and we have subtracted one from the other. And so we're comparing those differences, so that list. So technically we're doing a one sample test on two sample data. And that only works with this matched pairs. If we don't have matched pairs, if I just take, I'm going to take the AP data from Wasilla and compare it to the AP data from Colony, then we have to do a whole different type of two sample test, which we're going to talk about in our next chapter, chapter 10. If our conditions for inference are met, we can use one sample T procedures to perform inference on that mean difference. So a sample problem. For their second semester project in AP Stats, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during a week. So here's really good information. Different times during the week, because sometimes it may be slower or faster during different times. So we're making sure we're sampling all sorts of different times. They went to the same store and bought the exact same item. However, one of them would use the express lane and the other used the regular lane. And to decide which one they would use, they flipped a coin. So here's some random assignment in their experiment. If it was heads, Libby used the express lane and Catherine used the regular lane. If it was tails, Libby used the regular lane and Catherine used the express lane. They entered their randomly assigned lanes at the same time and each recorded the time in seconds it took them to complete the transaction. So here was the time in the express lane. Here's our time for the regular lane. And then what we do is we compare them. So I'm going to take regular minus express. And the reason why I'm doing that is so that a positive value means the express lane was faster. So if I lay that out beforehand and say, okay, I'm going to do regular minus express, which means that a positive value means this, then it makes things so much easier later on. So when you are interpreting your values, you know what you're talking about. So 342 minus 337 gives me 5, so on and so forth. How can we do this on the calculator? Great question. Okay, to do this on the calculator, we're going to have to come take a look at our handy dandy calculator. What I did is I entered in our express lane in list 1. and our regular lane in list 2. And so now when I'm looking at this, we've got express lane, regular lane, and I want to do regular minus express. So my regular lane is lane 2 or list 2. So I'm going to take list 2, see that? And I'm going to subtract list 1, and it tells me all those values. So now I can calculate all my stuff using everything in list 3. So now if I want to calculate a mean, I'm going to go to stat, calculate one variable stats on list 3, and I get a mean, I get a standard deviation, and I can use that values to help me calculate my information. So now we're going to go back and we're going to carry out a test to see if there's convincing evidence that the express lane is faster. So we're going to check, is the express lane faster? Let's see. So we will test the hypothesis that the express lane and the regular lane are the same speed. So we're going to see that there's no difference at 0.05 significance level. So our null hypothesis is that there is no difference, but we think that really the express lane is faster. And that's where it helps us to write that alternative hypothesis. Because remember, positive values means the express lane's faster. So then I'm looking for my positive values on that alternative hypothesis. And again, our mean is the actual mean difference in the regular lane minus express lane required to purchase an item at the supermarket. So what we're going to do is we're going to perform a paired t-test for means, meaning I'm using paired data from a matched pairs experiment, and I'm going to use just a regular t-test for means. So random. There were random times at the supermarket and randomly assigned lanes. So we're good. We covered all of our bases there. Normal, 15 is not less than or equal to 30. So we must check for outliers and strong skewness. So luckily I have that list 3 on my calculator. So we're going to head on back to the calculator. Oops. And on the calculator, we're going to go ahead and we're going to stat plot. And we're going to come over to our normal probability plot for list 3. We're going to graph and look at that graph. That graph looks really good. In fact, that's really linear, but I'm a little worried about that being an outlier. So how do I check outliers? I'm going to change that to a box plot. So I'm going to come to the modified box plot. And now we're going to graph that and look. We can even zoom 9. See, even looks better. There are no outliers because there's no little stars or dots at the end. So it's not an outlier. So now what we're going to do is we're going to go back to our thing and we have to show evidence. Evidence, is it normal? Yes, it is. So let's go ahead and sketch out that graph. So I'm going to have to go back. So I'm going to sketch this out really quick. It looks like, and there are no outliers. We double checked with our box plot graph, and linear, so no skewness. So our results are robust. Okay, independence more than 150 times that people buy things at the store. Also, random assignment and times assure independence. That's why we pick those random things, because what happens at one will not affect the other. So a lot of times with our experiments, that random assignment and the random times that we're picking helps assure that independence. So now it's the do part. So now we have to calculate our stuff. Luckily, we already did our one variable stats. So we knew that our X bar for list 3 was 42.6 repeated. And our standard deviation was huge. It was 84.01927. So now we're going to calculate our t-value. So 42.6 repeated minus this value from our null hypothesis divided by our standard deviation, which is divided by the square root of our sample size, 15, which gives us, what, 42.6 divided by 21.6937, which gives us 1.9637. And then we calculate our probability value. So the probability that our t is greater than 1.9367 would be a t-CDF, because it's a t-value, with a lower bound of 1.9637, an upper bound of really big, 100, and a degrees of freedom, let's see, 15 in our sample, which means our degrees of freedom is 14. This gives us a probability of 0.0349. So our conclusion, well, 0.0349 is less than 0.05. So we reject our null hypothesis, which means we have convincing evidence that the alternative hypothesis is true. We have convincing evidence that the difference is greater than 0, which means the express lane is faster. So it's a little different than what we were doing before, but not so much different. We're still going through the stuff. The hardest part is probably our hypotheses based on how we set up our subtraction. So if I did my subtraction the other direction, where it was express lane minus regular lane, which seems to make sense because it go left to right, then I would have to say all negative values mean that the express lane's faster. So then here, we would then say that our difference was less than 0 because it'd be negative, and our numbers would be slightly different, which is okay. Okay, about paired data. Individual scores will be dependent on each other, but the difference in scores are not dependent. So the difference list, those should not be dependent on each other. Those should actually be independent. But the individual scores are dependent on each other. Be sure to report degrees of freedom every single time. If subjects in an experiment were not randomly chosen, we can't generalize to the entire population. And if subjects in an experiment were not randomly assigned, we can't make an inference about cause and effect. So just reminding you about why we do all of this. And always remember that confidence interval will give more information than a significance test. So we could have taken the same data and done a confidence interval instead. Using tests wisely. Significance tests are widely used in reporting the results of research in many fields. New drugs require significant evidence of effectiveness and safety. Very important right there. Courts ask about statistical significance in hearing discrimination cases. In all cases, statistical significance is valued because it points to an effect that is unlikely to happen by chance. And that's the idea. Unlikely to happen by chance. Statistical significance is not the same thing as practical importance. Pay attention to the actual data. So plotting your data, looking for outliers, along with the statistical significance to avoid this. Foolish user of statistics who feeds the data into a calculator or computer without exploring the situation will often be embarrassed. If you were to actually graph the data, would it be worthwhile to calculate? Don't ignore the lack of significance. Usually more data will be needed to help us make some conclusions. When planning a study, verify that the test you plan to use has a high probability or a high power of detecting a difference of the size you hope to find. Statistical inference is not valid for all sets of data. Badly designed surveys or experiments will yield invalid results, and you have to start all over. You can't just redo numbers and adjust numbers. As soon as you have a badly designed survey or a badly designed experiment, you have to start all over. So always, when you're looking at other people's work, look at how the data was produced. How was that study designed? How did you get the information? Running tests multiple times to get the significance you want will have little meaning. So this is really trying to cheat the system, which is totally not cool. And that's it for Chapter 9.